Welcome to Archicraft, a bit of architect, your go-to podcast for modern software and solution architecture, enterprise strategies, and AI-powered engineering. Each episode is AI narrated, based on the original blog content by Dima Golodiuk at demongo.com.
You're listening to the 17th episode of the podcast. This episode is titled, How to Spot Bad Architects versus Great Amplifiers. In this episode, we explore how to tell a bad architect who just hands down verdicts from a great one who actually makes the room smarter. Let's get started.
Picture this. It's a Tuesday afternoon, you're sitting in a design review, and the air in the room is just incredibly stale.
Oh, yeah. We have all been in that exact room.
Right. Someone clears their throat and slides this dense 50-plus page document across the table. It is just packed with diagrams, arrows pointing in like every conceivable direction, boxes nested inside of boxes.
The classic monolith of a document.
Exactly. And the person who slid it over just looks at the team and delivers this simple, chilling command. Read this and build it this way.
It is the universally dreaded scenario for anyone working in tech, because that exact moment is where collaboration just completely breaks down and blind compliance takes over.
Yeah, the system is no longer being built to solve a problem.
Right. It's just being built to satisfy a mandate.
And that mandate and the person handing it down, well, that's the jumping off point for today's deep dive. We are digging into this really fascinating field guide written by Dmitry Golodiuk, who goes by Dima.
It's a great piece.
It really is. It's titled, How to Spot Bad Architects versus Great Amplifiers. And this deep dive is custom tailored for you. Whether you're a senior architect, a CIO, a CTO, or, just a developer trying to navigate the messy dynamics of your engineering team.
Because it fundamentally changes how you evaluate technical leadership.
Exactly. The core mission here is to help you distinguish between authority that was never actually earned, and real credibility that actually makes the entire room smarter.
Dima frames this whole thing as a battle between two archetypes. You have the oracle and you have the amplifier.
So to recognize an amplifier in your own organization, I'm guessing we first have to unpack the exact failure mode of the oracle.
Yeah, we do. And that takes us right back to that 50-page document sliding across the table. Dima actually talks about reading one of these massive architectural mandates cover to cover when he was new to the industry.
And I'm guessing it wasn't exactly a page turner.
Not at all. Half of the document was literally copy-pasted from internet forum threads.
Oh, wow, really?
Yeah. And the other half was just this rigid list of buzzword rules. Everything had to be, loosely coupled. Everything had to be cloud native.
Let me guess. Everything had to run on Kubernetes.
Of course. But there was zero actual reasoning attached to any of it.
So when the engineers, the people who had been building the actual system for years, when they asked why they needed to use those specific patterns, what happened?
The architect just shrugged and pointed to a slide number.
Okay, let's unpack this. Because the oracle is essentially just a pretender, right? They hand down absolute answers from this unquestionable position of authority.
They drop the document, deliver the verdict, and then they vanish.
Right. They disappear before they ever have to live with the consequences of being wrong. It's like having a terrible driving instructor who just reads you the manual out loud while the car is actively in a skid.
That is a perfect analogy.
Instead of, grabbing the wheel and showing you how to steer out of it.
Which leaves the engineering team completely holding the bag when those untested assumptions collide with reality.
Yeah, that's brutal.
It is. But, we shouldn't assume every oracle is just a con artist faking it with buzzwords.
Wait, really? Because they sound pretty bad.
Well, very often, oracles are actually genuinely experienced engineers. It's just that their knowledge has quietly gone stale.
Okay, so they're relying on authority they earned a decade ago.
Exactly. Which means they insist on outdated constraints. You might have an architect demanding that every single new application must be designed to scale out horizontally across, dozens of machines.
Which used to be gospel for handling heavy traffic, right?
10 years ago, absolutely.
Mm-hmm.
But today, a single well-specified server with modern NVMe drives and, a few terabytes of RAM could probably handle the entire workload of their business without even breaking a sweat.
So the oracle's advice was completely correct once.
Yes, but they never bothered to check if the underlying physics of the hardware had actually changed.
They stopped learning. So they just enforced the rules they memorized back when they were still writing code every day. The software developer Joel Spolsky actually coined a brilliant term for this back in 2001. He called them architecture astronauts.
Oh, I love that term.
Yeah, these are leaders who float up to this very comfortable, totally useless altitude of pure abstraction. Up there in orbit, their sweeping visions sound incredibly sharp.
But when you try to bring their designs down to Earth and actually build them,
You realize there's no oxygen. There's no practical foundation.
and this is exactly why Demas leans on a quote from Gregor Hohpe, a highly respected enterprise architect. Hohpe says that architects shouldn't try to be the smartest people in the room.
Their entire job is to make everybody else smarter.
Exactly. That is the fundamental definition of an amplifier.
But, I mean, making everyone else smarter is a great metric on paper. If you're a CTO listening to this and you're trying to evaluate your own architecture team, you can't just look at a diagram and know if it was drawn by an astronaut or an amplifier.
Right. It doesn't work like that.
So how do you actually measure if someone is making the room smarter?
Well, Dima introduces a fantastic heuristic for this, again borrowed from Gregor Hohpe. It's called the rubber duck test.
Hold on, the rubber duck test. Because I've seen developers do this. Rubber duck debugging is a classic solo trick.
Yeah, it usually is.
A programmer gets stuck on a bug, so they literally explain their code line by line to a little yellow plastic rubber duck sitting on their desk. The act of explaining it out loud forces them to slow down and usually helps them spot their own mistake.
Right.
But if an architect is playing the duck, aren't they just passively sitting there in silence while the team does the actual work? That doesn't sound like they're adding much value.
Well, if they were just a passive listener, yeah, that would be completely useless. But Hope's version is an active human rubber duck. It's a measure of team behavior.
Meaning what, exactly?
Basically, do engineers voluntarily bring you their problems? Because talking to you makes them think better. You aren't giving them a prepackaged answer.
Okay, so what are you doing?
You're asking highly targeted questions, offering a hint here and there, shifting their perspective, and really just drawing the solution out of them.
So they aren't a mandatory checkpoint you have to clear for compliance. They are a resource you actively want to utilize.
Exactly. And the mechanism behind how they achieve this is what Hope calls the phantom sketch artist.
Phantom sketch artist. Okay, break that down for me.
Think about a police sketch artist. The artist wasn't at the scene of the crime, right? They have never seen the suspect.
Right.
What they do have is a deep underlying knowledge of human facial anatomy. They know how the distance between the eyes relates to the cheekbones, and they use that anatomical knowledge to ask the witness the right questions.
Pulling the description out of the witness's head.
Yes.
Yeah.
Translating those fragmented memories into a highly accurate, usable drawing.
Because the witness has all the raw information, but they can't draw.
Exactly. The engineering team has all the specific domain knowledge about the software they're building, but they might not see the overarching structural patterns.
So the amplifier architect is the sketch artist. They extract the domain knowledge the team already possesses and reflect it back in a form the team can actually build from.
Right. But to be a good sketch artist, you have to relentlessly study anatomy first. You just can't fake it.
Because you need to know what questions to ask.
An architect has to have real, grounded technical chops to ask the right questions about system design. They need to understand data flow, concurrency, and failure domains.
But here's where it gets really interesting. If the architect is essentially just sketching what the team already knows and organizing it, why do the resulting systems still so often become tangled, fragile messes?
It's a great question.
Because getting to a simple sketch seems brutally difficult for most organizations.
Well, it's because we have a fundamental misunderstanding of what simple actually means in technology. We tend to treat simplicity as the default state of nature.
Like we assume that if we just don't overthink things, the architecture will naturally be simple.
Exactly. But Dima argues the exact opposite. Simplicity is the most expensive thing on the table. You don't stumble into a simple architecture. You have to ruthlessly engineer it.
You know, I think about this like designing a physical space.
Yeah.
A beautifully clean, minimalist, modern room isn't a natural occurrence.
Right. A natural room is full of clutter.
Yes. If a room looks perfectly simple, with no wires showing and completely clean lines, it means someone spent days tearing down drywall, routing electrical cables inside the walls, and building custom hidden storage compartments.
It looks effortless, but it took immense hidden effort to achieve that simplicity.
So how does that apply to software architecture?
In software, we categorize that hidden effort by splitting complexity into two distinct buckets. First, you have accidental complexity.
Which is the equivalent of the drywall scraps and cables running all over your living room floor.
It's the bad stuff: glue code, mismatched tools, poorly chosen frameworks that just fight against each other. You want to eliminate accidental complexity entirely.
Makes sense.
But then you have essential complexity.
That would be the physics of the problem itself.
Right, yes. The essential complexity cannot be negotiated away. If you are building a distributed system, say a global banking application, you are going to have to deal with the speed of light.
You will have network failures.
You'll have to build in retries, manage data consistency across continents, and handle back pressure when a server gets overwhelmed. That isn't accidental. It's inherent to the fact that you are trying to make computers talk to each other across an ocean.
You can't just pretend the cables don't exist. You still need electricity to run the house.
Exactly. And Dima brings in Einstein's famous rule here, repurposed for systems. Make things as simple as possible, but no simpler.
So a bad architect tries to paper over the essential complexity, hiding it behind abstractions that eventually leak and break.
While a good architect conquers it, they make it intuitive for the engineers to safely work within that complex environment. Because when you fail to manage that complexity, you hit a ceiling defined in the book Team Topologies as team cognitive load.
The mental capacity a team has to understand and safely modify the code they own.
Right. And once unmanaged complexity pushes a system past that cognitive limit, delivery just grinds to a halt. The code instantly turns into legacy code.
Wait, instantly. We usually think of legacy code as just being old.
In this context, legacy code is simply code that has exceeded human working memory. Everyone is suddenly terrified to touch it because nobody can hold the entire system in their head anymore.
Legacy code is just code that broke the cognitive limit. That makes so much sense. But taking ownership of that complexity and paying the steep price for simplicity is incredibly difficult.
Very difficult.
Which is why sometimes doing it wrong is actually the right business decision, right? Dima talks about the big ball of mud.
Yeah, the big ball of mud is a term coined by researchers Brian Foote and Joseph Yoder. It describes the haphazard, duct-taped-together shape that most systems actually end up taking.
Well, what's crucial for executives to understand is that sometimes a fast, ugly, messy system is the correct trade-off.
Absolutely. If you are a startup with 3 months of runway left, or you have a brutal deadline to beat a competitor to market, the big ball of mud might save the company.
And an amplifier architect doesn't pretend the mud is a beautiful minimalist room. They admit the trade-off out loud.
They document it. They say, look, we are taking on this mess intentionally to survive today, and we will have to pay down this technical debt tomorrow.
They own the reality of the situation. But, you know, taking ownership of a messy compromise is incredibly uncomfortable for a large corporation.
Oh, they hate it.
Most executives don't want to sign their name to a big ball of mud. So when organizations want to avoid making those tough binary calls, they diffuse the blame, they form a committee.
And we see this failure mode constantly. Gregor Hohpe actually coined a term for it, Gregor's Law.
Let's hear it.
It states that excessive complexity is nature's punishment for organizations that are unable to make decisions. When a committee tries to avoid offending anyone, they choose compromise. And in engineering, compromise is often far worse than either extreme. Dima highlights the historic ATM cell size debate from the 1980s to illustrate this perfectly.
ATM, that was a global effort to standardize network data packets, right?
Yeah. Global telecom networks were trying to agree on a universal standard size for data packets moving across the wires. The United States contingent wanted 64-byte cells.
Because they were optimizing for data transmission.
Right. When sending data, you want larger payloads so the overhead of the packet headers doesn't eat up all your bandwidth. But the European contingent, they wanted 32-byte cells. They were optimizing for voice transmission.
And voice traffic is constant, but requires incredibly low latency.
Exactly. If a packet is too big, you have to wait to fill it with voice data before sending it, which introduces delay and causes severe echo cancellation issues on phone calls.
So you have two completely valid but competing essential needs: data payload efficiency versus voice latency.
And the committee spent forever arguing. Neither side wanted to concede. Finally, they reached what they thought was a diplomatic compromise.
Don't tell me they just split it down the middle.
They split the difference exactly down middle and settled on a 48-byte payload.
Oh no. Which means it wasn't big enough to be efficient for data, and it was still too big to prevent echo issues for voice.
Yep. It was the mathematical average of two good ideas, resulting in a standard that optimized for literally no one.
That is painfully funny.
Dimmo points out that Ken Thompson, one of the pioneers of computer science, leveled the exact same critique against the C++ programming language.
Really? C++?
Yeah, C++ was shaped by committee consensus to preserve everyone's options. They tried to appease the low-level memory managers who wanted bare metal control, and the high-level object-oriented programmers who wanted deep abstraction.
And as a result,
they created a massive bloated syntax where there are like 5 different ways to do the exact same thing. It created a massive cognitive load for future developers because the committee refused to have a single coherent point of view.
So what does this all mean? Does this mean a good architect just has to be a dictator to avoid committee design? Like, do they just slam their fist on the table and say, we are doing 64 bytes, end of story?
Well, no, the amplifier doesn't force agreement through dictatorial power. Instead, they expand the solution space before the argument even begins.
How do they do that?
Let's take the most tired recurring argument in modern software engineering: microservices versus the monolith.
Oh boy. Half the room wants to break the system into tiny independent microservices for clean code separation.
And the other half wants to keep it all together in one giant monolith application so they don't have to deal with network failures and deployment nightmares.
So a bad architect either picks a side, creating winners and losers, or they compromise and create a tangled mess.
But an amplifier steps in and reframes the conflict. They point out that the room is actually conflating two different things. They split the debate into 2 separate questions.
Which are?
How modular is the code when we build it, and how is it deployed when we run it?
Oh, interesting. So if they separate build time organization from runtime deployment, it sounds like they're trying to get the clean boundaries of microservices without the nightmare of deploying them independently. Are they just proposing a highly organized monolith?
They are proposing a modular monolith. The code is strictly organized and modular when the developers are working on it, which satisfies the microservice advocates. But it compiles and deploys as one single unit at runtime, which satisfies the monolith advocates.
And almost everyone in the room looks at that new option and realizes it solves both of their core concerns.
Exactly. The architect didn't dictate the answer. They held the frame. They ensured the team was actually arguing about the exact same variables, which allowed the engineers to discover the superior hybrid option themselves.
So they functioned as the phantom sketch artist again. They just drew a more accurate map of the territory so the team could find their own way out of the woods.
Precisely.
Now, conquering essential complexity, dodging the committee trap, and expanding the solution space, all of this drives toward one foundational metric. If a CIO is evaluating their architecture team, what is the core value proposition they should be looking for?
If you strip away all the diagrams, the technical vocabulary, and all the Kubernetes buzzwords, the true pitch of an architect to the business is 3 words: I lower risk.
But we have to be specific about what kind of risk, right?
Right.
Because architects often ignore half of the equation. First, there is execution risk. Can we build this on time, on budget, and will it crash in production?
Banks and highly regulated industries obsess over execution risk.
Ensuring the bridge doesn't collapse when the wind blows.
But there is a second type of risk: product and market risk.
Right. Does anyone actually want this thing we are building? Does it solve a real user problem and generate revenue?
An architect who only focuses on execution risk might perfectly design a system that scales to millions of users and boasts 0 downtime. But if nobody wants the project is still a catastrophic failure.
You essentially engineered a perfectly stable bridge to nowhere.
Exactly. Which brings us to Martin Fowler's brilliant formulation on architectural value. Fowler argues that an architect's value is inversely proportional to the number of decisions they make.
Wait, the fewer decisions an architect makes, the more valuable they are.
Yeah.
That feels counterintuitive. If you are paying someone a massive salary to be the chief architect, shouldn't they be making all the critical decisions?
Making every call correctly up front is an impossible standard because you cannot predict the future.
Right.
The real job of an architect isn't predicting the future. It is eliminating irreversibility. It is making it cheap and easy to walk back wrong calls.
If you design a system where changing your mind next year requires rewriting 2 million lines of code, the business risk is massive.
But if you design a system where changing your mind just means swapping out one isolated component, the risk is incredibly low. A great architect defers decisions until the last responsible moment, keeping the company's options open so they can adapt to market feedback.
Okay, I have to bring up the unavoidable elephant in the room here regarding documents, diagrams, and synthesizing knowledge. Generative AI.
Yes.
If I have a modern LLM, I can tell it to draft a 50-page architecture document in 10 seconds. It will be incredibly articulate, full of best practices, and perfectly formatted. If an AI can do that, doesn't that make the human architect obsolete?
Dima references Hohpe's exact take on this dynamic. If you use an LLM to generate your architecture document and you just hand it to the engineering team as an unverified mandate, you haven't lowered the risk.
You have just relabeled it.
Exactly. The LLM in that scenario is the ultimate digital oracle. It speaks with absolute unearned confidence, it hallucinates based on its training data, and it absolutely will not be there to fix the production outage at 3 a.m. when its design fails.
The AI just replaces the guy dropping the document on the table and disappearing. It's just an oracle that generates 50 pages of buzzwords faster.
But if a human architect uses AI as an amplifier of their own abilities, using it to quickly explore different solution spaces, to check their blind spots, or to draft the boilerplate documentation so they can spend their actual time deeply engaging with the engineers, then the dynamic flips entirely.
So the AI exposes the oracle architect as completely obsolete because the bot can do their shallow job much faster.
Yes. At the same time, it makes the true amplifier architect more valuable than ever because they are the ones validating the real-world constraints, understanding the market nuances, and actually lowering the business risks.
The tool doesn't replace the sketch artist, it just gives them a faster pencil.
That's a great way to summarize it.
So if you're sitting in a design review later this week, look at the architecture diagram on the screen. Ask yourself, is this essential complexity or are we just generating accidental complexity?
And when someone slides a heavy document across the table and tells you to just comply, run the rubber duck test on them.
Right. Are they actively making you smarter about your own problem? Are they helping to draw out the knowledge your team already has? Or are they just a gate you have to get through, an oracle handing down unquestionable laws?
It leads to a final, lingering question I'd love for listeners to ponder on their own.
Let's hear it.
We established that a great architect's real job is lowering risk by making decisions reversible. How does that fundamentally change how you interview and hire tech leaders?
Usually in an interview, we ask candidates to walk us through their most successful design, right? We want to hear about their grand vision and their flawless execution.
But if the goal is eliminating irreversibility, success looks very different. Perhaps the most revealing question you can ask an architect candidate isn't about their victories.
So what should you ask?
Perhaps the true test of an amplifier is asking, walk me through the worst design you successfully walked back.
Oh, wow. Proving that they engineered the system to survive their own mistakes. It totally flips the script on what we consider success in tech leadership.
It really does.
Thank you so much for joining us on this deep dive. We hope it gave you some powerful new tools for your next design review, and we will catch you on the next one.
Thanks for tuning in to Archicraft. This episode was generated using AI from Dmitro Golodiuk's blog at demongo.com/news. If you enjoyed this episode, follow the show on your favorite platform and share it with fellow architects and engineers. Until next time, build smart, architect with intent.